as we've heard before today, leaves play a very important role in the traction, and this is down to 0.03. We have down on the right side, you see results from laboratory testing, where you can see that dry and wet leaves are the lowest traction. And this has been known for quite a while. The oldest paper that I found was from 1973. And in 2004, the RSSB, the Australian Safety and Standards Board, did a review on low adhesion phenomena, and they figured out that two main reasons for low adhesion were leaves and low amounts of water. And especially leaves became a very interesting topic. There was quite a research done by University of Sheffield, University of Technology in Brno, KTH, also Knorr-Bremse, with twin disc tests, full-scale tests, pin-on-disc tests. But a little bit of lack was, when we looked at the literature, vehicle tests and traction characteristics investigated by vehicle tests. So we thought, why not do this by ourselves and see if we can come up with, because scalability from laboratory tests to vehicle tests is always an issue, and at the end you have to compare them in some kind of way to see how valid they are. And so we went to the test center VUZ in Velim in Czech Republic, and we had 2 days in autumn where we could perform the measurements. The first day there was a little cloudy in the morning, and then during the day there was sunny, and it was temperatures in between 6 and 10 degrees. And we consider this dry in case of this presentation. This will be the baseline. And on the second day, there was some dew on the rails in the morning, very high humidity, almost 100%. And during the day, it started to rain. So we consider the morning of the second day as damp, and the noon, around noon, was wet conditions. So we had 3 different contact conditions. And and we conducted these experiments with Siemens locomotives, and with the help of Siemens, we had 2 locomotives, one to keep the speed of the locomotive constant, and the other one was our measurement locomotive, where 3 axles were in pure rolling, while 1 axle was controlled with a modified creepage control, where we started at 0, went up to a maximum creepage, and back down to 0 in 22 seconds to get a traction characteristic. And we did this on different parts of the test ring. And here are the baseline results for dry conditions. It was measured on locations surrounded by farmland. And you can see the results for 3 different speeds. Down is the x-axis is the anonymized creepage, where we had the creepage values divided by the maximum creepage values, and then the anonymized traction value, where we had the traction value divided by the maximum traction value. And these curves, they look very similar, especially at the beginning. When you start, you got a very high increase. Then you got a moderate increase. That's a little different for the different velocities. In the gray one, you can also see a hysteresis. This is because the track is not uniform. There are always some stuff on the track, and if you measure something, you get all different kinds of stuff in there. Nevertheless, what you can see is that there are 3 different maxima depending on your speed. For the higher speed, it's on the left side, more on the left side, and for the lower speed, it's more on the right side and also higher. And then you got a decrease that's also depending on also on temperature, but on velocity. And and also you got some drops in between, especially for the red line. If you imagine you got 22 seconds where you change your creepage from 0 to the maximum and back again, and you're going with 20 meters per second, you just have a longer distance that you measured, and if there's stuff on there, then you can see this in these measurements, if there's some changes on the rail or something. And this is baseline for farmland. The more interesting results is when we go to a forest. And here we had one part of the track. You can see the satellite pictures. We had 4 different measurements. The green and the yellow one, they are directly in the forest, while the blue and the violet one, they are at the exit of the forest. In white, you can see the traveling, the direction in which the locomotive was traveling. And down on the right side, you see again the creep curves, and you see the green one and the yellow one, which were measured in the forest. They are relatively low, in between 20 and 50%. And once you get to the blue one and the violet one, you see that there are peaks and there is a higher traction. So we wanted to look at this closely. And we said, let's plot this over the track distance and see where exactly the low traction was and where the high traction was. And there you can see in the forest, there's always the low traction. But as soon as you exit the forest, you got these peaks. And in the forest itself, the values are in a small window and are comparable, while at the exit of the forest, there's this peak. And then a few meters or a few hundred meters after this peak, there again are low values. This was very interesting, and keep this in mind that in the forest they were relatively constant, or there was a small variation for dry conditions. Now we come to damp and wet conditions. This was measured on a different location, and the location where we measured the damp and the wet in green and the damp in blue. You can see there's a small overlap, so it's a little bit difficult to distinguish between effects coming from the location you're measuring at and effects that are caused by the conditions, but nevertheless, we compared them. And you see that for wet conditions, the green one, there's a higher variation of what could happen, and also the curve, the mean value, it's flat, relatively flat, while for damp conditions, you can see that the values are very close together with a maximum for low creepages, and it goes down a traction loss for higher creepages. This is also something that we've seen in the RSSB T1077 project, which was focused on water-induced low adhesion, where we could also see that once you have low amount of water in the contact, then you have this first peak, and then it goes down with traction loss for high creepages. While for high amounts of water, you have more of a flat curve. So this was a very interesting result, and also comparable to the literature. If you go to the forest now for damp conditions, then you see a different picture. You can see all kinds of different things that can happen in this forest. You can see values that are down there at around 30 or 20%, while you get also values that are comparable to, I don't know, dry conditions. So you got some things that start low, go back to high, and then go back at a high value. You get some that are starting at a high value and go back to low value. We also tried to map these to the track distance, but we didn't find a real reproducive effect. So what we figured was that in this forest, when there is a little bit of water or different amounts of water, damp conditions, you don't have a uniform layer. You have your trees, the crowns of the trees, you got your rain, and some parts of the rail will be covered by rain, while others will be spared from the rain because of the crowns of the trees. You got shadows from the trees. They're also not uniformly distributed, so you get all different kinds of stuff that can happen in the forest. We then tried to find out with statistics to see if we can somehow map this, or if we can come up with some kind of statistic for these things. And what we found was for dry and farmland, for our baseline, we had the highest value. Here's in red, for those not familiar with box plots, this is the mean value of the distribution. This is where the most values are, and these are just some occurrences that are just sometime occurring. I don't know the English word at the moment, I'm sorry, but I'm sure you will know what I mean. For dry forest, you see that the mean value, as soon as you leave the farmland and go to the forest, you got lower values, lower mean values. These are the values from the exit of the forest. This is why there are some higher ones as well. For damp and farmland, you get higher values than in the forest. While for damp and forest, this is where we had all these different variations, and there you can get everything from from forest values to the farmland values, there's everything in between, and then at the end, the wet values. With farmland, they were the lowest ones, but you also have to keep in mind that there was a lot of variation for the wet ones. So what the statistics, or this statistic does not show you, is the distribution of the creep curve, how it goes from small creepages to high creepages. These are is a summary of all the values, a statistic over all the values we measured. So you have also to keep in mind the shape of the curves as well. We then tried to compare the results to our models, especially the ECF model, which was also developed by Virtual Vehicle. First, we used the model as it is and compared it to the dry testing. You can see this one here, and I think it's quite a good fit for all 3 different speeds. And then we used the other values, or the other results for damp, wet conditions with farmland and forest to parameterize the model. And while there's a good agreement in case of wet and damp surrounded by farmland, the wet, or the one in the forest, there is a variation, and as I said before, there is some randomness, some stochastics in there. That's why the curve does not fit as good as the other ones, but still quite good agreement, I think, overall for the model. Yeah, and now to summary. We did vehicle tests with the help of Siemens, and the local influences and the track where you are, the track position, play a huge role. And you have to make sure, or you have to make as sure as possible that you always compare the same location and not different locations with each other, because then you have additional influences. Higher speeds lead to lower traction values. This is also known from the literature. For farmland, dry was the highest, and damp was in the middle for low creepages, but if you went to high creepages, then it suddenly was the lowest one, while wet was the lowest for low creepages, but in the middle, in between dry and damp conditions for high creepages. And in the forest, at the forest axis, there was a high traction, while in the forest, there was a high variation, especially compared to farmland, and there were also lower values possible than in farmland. And at the end, we compared it to the model, and I think it was quite a good agreement and used for further parameterization of the model. So, thank you for your attention.